Hello, y'all. Welcome to lesson 91 of my DB chemistry curriculum. Today we're going over reactivity 2.3.5. This is an HL topic. In this section, we're talking about the reaction quotient Q as it's calculated using the equilibrium expression with non-equilibrium concentrations of reactants and products. By the end of this, we'll be able to calculate the reaction quotient Q from concentrations of reactants and products at a particular time, then determine the direction in which the reaction will proceed to reach equilibrium. So with that said, let's talk about the reaction quotient Q. So as stated in the beginning, very importantly, this is a non-equilibrium value. So we use Q anytime we're not at equilibrium. And what it is a ratio between the concentration of products and the concentration of reactants. Now, this may sound very similar to another ratio between concentrations of products and reactions, such as maybe the equilibrium constant, which is actually what we use it for. We compare with our equilibrium constant Kc to determine which way a reaction will progress, either to the reactant side or to the product side. So given our reaction A plus B reacts within an equilibrium system to form CC plus DD, we will find our reaction quotient Q as C to the power of C times the concentration of D to the power of D divided by the concentration of A to the power of A times the concentration of B to the power of B. It is the same equation as QC, or sorry, as KC, same equation as our equilibrium constant, but not at equilibrium. That's the big difference. We use Q whenever we're not at equilibrium. So how do we actually use it? How do we actually compare these values? Well, let's start with an example, and we'll kind of end with this example too. So if we look at the reaction of N2O4 as a gas, decomposes into two nitrogen dioxide gas molecules, and we know that the equilibrium constant at a given temperature is 41.0, and we also know the current values or current concentrations. We'll say the current concentration is 2.00 mole decimeter cube inverse, and we'll say the current concentration is 6.00 mole decimeter cube inverse. We can now use the reaction quotient to predict the direction of this reaction, predict whether we'll make more products or make more reactants. So we'll plug it into our equation Q, which will be NO2 concentration raised to the power of 2 divided by the concentration of N2O4. Plugging in our values, we have 6.00 squared divided by 2.00, giving us a value of 18.0. So you'll notice that our value, Q, is less than Kc. In this case, that means our value on top is either too small or our value on the bottom is either too big. But the only way to rectify that, to get to a larger magnitude to reach our equilibrium constant, is to produce more products. If this number becomes larger or this number becomes smaller, which happen at the same time as this reaction progresses, our Q gets larger. So we know that therefore this reaction will progress to the right, the product side, in order to reach equilibrium. So that's what the reaction quotient Q allows us to do. We can predict where in our reaction we are and what must happen so that equilibrium can be achieved. We can just simplify this at the end by just saying if our Q is less than Kc, we know that we know that our reaction progresses to products. If Q is greater than Kc, then the inverse reaction progresses to reactants. And turns out if Q is equal to Kc, we are at equilibrium. So this is the reaction quotient. I hope this helps and have a great day.